One of the good thing about Rudin is that it always looks challenging. It wasn't the wonderful. So like 1 to 10, very good skills. 1 to 10. Because again, related to series it will be enough. Patience. You need to at least in the level. So let's move ahead and then I like to, as I said, as I promised previously, that I'll like to return back to the compactness.
Beside the
Okay, this part I'm going to cover. This part of compactness I'm going to cover for model, grammar of analysis. You can also do things from in the terms of metric spaces as well. But I'm expecting that hopefully you're going to do this in topology. So, are you doing it in topology?
yes.
Metric spaces. You haven't done compactness.
No,
We'll do it. What you're doing these days in
topology. Spaces. Spaces, bases,
The bases and sequences and topology base. We are moving to
Ostrov spaces.
And we'll see that you are doing things in the terms of taking spaces. So these results that we are doing in R, that's from model, they can be analyzed with space level. So if you do those results in metric spaces, it is probably fine. If not, okay. So I'm assuming that we all know what are open sets, closed sets, what are limit points. So this basic machinery they have done it in GP. So I would like to begin with a characterization of closed sets, very important and very interesting characterization of closed sets. And this is that, and then I'll move to the compactness. So a subset of R as in C is a subset of R. Then C is closed F around F. This result can be generalized to B as well. C is closed if and only if you pick a sequence from C, it should converge inside C. Because any sequence from C should converge inside C. For every convergent sequence, Kn.
So when it is something
In C. Okay, when I'm saying that that's a convergent sequence in C, it means that all terms are in C. We have its limit, because if this convergent is going to converge to something, whatever that limit is, that limit lies the options. If that is closed in R, then and you pick any sequence, convergent sequence in that set, the limit of that convergent sequence is going to also be in that set.
from previously.
What was that?
Sequence was converted P that P should be in that case.
We did the completeness of R.
But generally we defined it.
How we define it?
We defined for convergent sequence is converting P. This is also next and that point is also this. So we said that that's
Complete. So we moved then for whole R actually. So we proved that R is complete. But here we're not talking about R,
subset
we're talking about subsets of R. In other words, you are going to have this completeness in closed subsets of R. That's so that previous result become a particular case of this. If you see, because R itself is a closed set. But in completeness, actually, which we say that every partial sequence should have one.
at first we defined every partial cell will.
Different. You have to be careful.
So we cannot say R is closed. R is not closed.
It is both happening.
It is closed. This closed and open.
It is both with respect to the immediate nature.
Okay.
Okay, so some version of it, basically, if you remember. Let's do this side. Okay. Assume that C is closed. Now, like take sequence. Let An be a sequence in C such that An converges to be F and G. Okay? And we claim
It wants to see.
that A belongs to C. So my trick is going to be this. The trick is going to be that I'm going to prove that this A
Since C is bounded, C is bounded.
by you will prove it. Not all closed sets are.
Every convergent. C is closed, so then
Why do those things? Close, okay.
Is R bounded?
Let's recall the definition of closeness. I assume that you remember the definition of closeness. What was the definition of closeness? Definition of closeness was that a set is closed if it contains all of its elements. A set is closed if its complement is open. There are also characterization. Closeness doesn't mean closed interval. You can have closed sets which are not necessarily closed. We claim that this A should belong to
We can prove A is limit point of C.
That's what I'm going to do. That's what I'm going to do. My claim is that this A is going to be the limit point of C. And in order to show the limit point, what I need to do?
For all
I need to take a neighborhood of
A.
A, and I need to show that neighborhood
Intersects with
intersects with what?
C minus.
C minus
C minus I. C minus A.
Then A would be a limit point, and then C contains all its limit points, so A would be bound.
In sequence, if you think unit
Do this. We can argue in this way. I can do much of practical ways. So we claim that A belongs to C. So now there are two possibilities. So should be in C. There's no other option. My point is that either A is going to be a term of this sequence, or it's not going to be a term of C. Because it can happen that this sequence is what? That's a constant. Then the element is going to be within that sequence. So if A is equal to AK for some K belongs to N, something belongs to N, then you are done actually. Why?
because all terms are in C.
Because all terms are in C actually. Hence A is in C. Okay? Then K belongs to
C.
Constant sequence.
for necessary that it should. But I'm saying that the limit can be inside the sequence, okay? So it could be term of a sequence or it couldn't be term of a sequence. So if it is term of the sequence, then it's already in C actually, because all the sequence is in C. So next is going to be that, okay, imagine that this is not the case. Otherwise, consider this. For every epsilon positive, if the sequence is convergent, there exists capital N such that such that An minus
Yes.
X is less than F.
A.
So An minus A is less than F or more than greater than or equal to 0. In particular, if I take N to be equal to N, it will follow that this capital An minus A is less than then this implies that An belongs to what? A minus epsilon and A. And what does this show then? Doesn't this show that A is a limit point of C? Why? Because A minus epsilon and A plus epsilon, so it's like this interval is a neighborhood of A. Okay? And every neighborhood of A, no matter what epsilon you have, how small or big, every neighborhood of A contains a term from C other than A actually. So that's what you wanted actually. समझ आ रही है?
Yes.
Because when you are saying that every neighborhood intersects with the set minus that point is non-empty, you are saying that every neighborhood contains some points of sets. Other than
How do we know that this is not A?
because we have assumed the case otherwise. We know that A does not agree to any of the terms of the sequence cells. So A can't be A. So, if this is the case, what does it shows? That A is a
C.
right? I am on the right.
Sir, C
Yes,
is
sir.
close.
Yes, sir. A is the limit point of
A is the limit point of A and
A is limit.
C.
Below that,
If C, since C is closed, so A is contained in C.
change.
सही है.
Once you are done with this, if you have this, you are done with the forward part. Okay, so this implies that A belongs to C. Okay. But if A belongs to C prime, then we know that for such C, C prime is contained in C. Therefore,
सही.
what's the definition of a closed set? Take a limit point of that set. That limit point is part of practically that set. What I did actually, I said that An is converging to A, and this A is a limit point of C. So if it is a limit point of definition of closedness, this limit point must belong to C. And that's what you need to prove, that I took a sequence which is converging to some point, and that point becomes the limit point of the closed set C and hence belongs to C. Let's move to the next one. Did it make sense? Now questions you ask me. So this is a very important characterization.
सम लिखा ना.
सर ये तो सिर्फ एक नेबरहुड के लिए है ना.
सही what epsilon C prime is the set of all limit points. C prime is set of all limit points. So if this is true, then A must be an element of C prime. But since C is closed, then C prime is a subset of C. Therefore, it must be okay. Think about the converse side.
So
In other words, we have now what? We have that every sequence in C that is convergent should converge in C. And from that I would like to prove that C is closed. In other words, I want to take a limit point, okay, of that set C, and I like to prove that that limit point is convergence. So the way is going to be this. I'm going to take a limit point x, and I'm going to construct a sequence x, which is going to converge to that limit point. And since the limit, like my assumption, since the limit of every convergent sequence is in C, that's what is going to be the result. So let x, let A be a limit point of C. Okay? Or we need to show that.
A be limit point of C.
We need to show what we need to show.
Which
That
is
A belongs to C. Okay?
So we show C is closed. That's how you. Say
Contains all of its limit points.
Say
That's what the definition of closeness is. That it contains all of its limit. So I took a limit point, and this A, okay, in the X actually, interpret A as a English letter A. Okay. Anyway,
for every limit point we have a sequence.
so we need to find a sequence actually. So if it is a limit point, what does it mean?
Resume करना है वो C में है for every convergent it resume करना है
So every neighborhood is going to contain some points of C actually, other than X. Okay? So as X is a limit point, so every neighborhood which is going to be of what form? X
Minus epsilon.
epsilon, X plus epsilon, and then equals points of C other than X. Huh? ठीक है? In particular, I can choose, let us choose, so this is true for all epsilon. So this is going to be true for epsilon equal to 1 over k as well.
K is
Where k is some nothing. Yes. Basically, if you see, we have done this kind of version of proof. So imagine I have this set, this.
Sir, for every
And
limit
I have a limit point here.
G, sir.
And I'm going to draw a ball of radius 1 over k on this point and going to choose a point from it. It can't be that much away. It should be really near to it. Only. Okay. And then I'm going to draw another ball centered at this point of radius and going to choose a point from it. And another ball going to choose a point from it. Then these terms are going to be as the That's what
We had done for this.
we have done it. So choose xk from every neighborhood x minus k over x plus 1 over. And my claim is that this xk is going to converge.
done.
How? Okay. X k is between x minus k and 1 over k. And this means that x
K
minus or xk minus x should be less than or equal to.
So which is there the next?
It's equal.
It's less than epsilon or maybe, which is sufficient for our purpose. So I can choose k as much as big I want. So I can make them near as much as I want. So you can choose as much as bigger. And if you keep on choosing k bigger and bigger and bigger, this is going to get nearer and nearer and nearer. Okay. So this means that this xk converges to x. So if it is converging to x, okay, and we know from hypothesis that limit of all convergent sequences
R and C.
are in C, so this is going to belong
X belongs to C. X is closed. C is
But we haven't put sir xk is in C.
Huh?
The sequence is in C.
It is in C actually.
We are taking it from
We have,
we are just taking it from neighborhood. We should take it from neighborhood.
but this neighborhood is going to intersect with the set C.
Sir, intersect to C से
Okay,
करेगा.
let's
हाँ.
write it. C minus x.
Yes, sir.
Okay.
Yes. Right, sir.
What does this beautiful theorem tells you? That not only R is complete, but R is a closed subset. We'll have that. It's like closeness can be characterized in the terms of convergence. That if you have a set in which every sequence is converging within that set, should be closed. And this, if this is not happening, so we just think about the negation of this basically. So how much powerful is that? So you want to prove that a set is not closed.
Just take a
Just take a sequence within it and show it is convergent and limit is not in the set.
out
You're
to
done it.
something.
Suppose something very powerful. For example, this is not closed. Why this is not closed?
Always.
Because it does not contain all its limit points.
I can take lots of sequences, so 1 over 2n in 1 over n. Okay. So it converges to 0. 0 is not in the set.
Yes, sir.
Therefore, that's not a closed. Always think about negations and give you also. Alright. Basically, where we are heading, and what is our key thing that we want to do? We want to prove something which is called the Henry-Borel theorem, okay? Which is kind of a characterization of compactness. So it's a characterization which says that a set is compact in R and in general in metric spaces, if and only if it is closed and bounded. That's it. We just prove it is closed and it is bounded, sufficient for storing its compactness.
Boundedness of set.
We have defined it. It's like in R, we can say a set is bounded if you can have an interval, closed interval which contains.
Signs for boundedness.
Anyway, so let's move ahead. Let's get this result of Henry-Borel theorem and we'll put this theorem in the terms of lemma set.
And
A series of lemmas.
bound.
Now, this result, Henry-Borel theorem, will simply say that If they have a closedness of something and boundedness of something is going to give you the compactness. And in meter space. General, it's not necessary that it should be true in R. The thing about Rudin is that it proves it in meter spaces. If you want to do it at least enough, you'll see that if you're doing